Look at how these geometric panels continuously shift and reorganize. This visualizes the core tension in modern UI engineering, the struggle to manage spatial boundaries as data density changes across different screens. The navigation rail solves one side of this problem, designed for rapid, top-level context switching, utilizing a compact vertical footprint to preserve maximum screen real estate for the primary content. However, as data density increases and navigation requires depth, a single vertical strip of icons lacks the capacity to represent nested parent-child relationships. Supporting these structures requires the multi-level sidebar tree. To support these divergent user experiences, engineers usually build two completely independent layout engines. That requires maintaining two codebases, two sets of geometry rules, and doubling the layout bugs. Eliminating that redundant architecture requires a single, unified spatial container, a layout engine capable of dynamically swapping UX paradigms on the fly based on the strict requirements of the data payload. In the B4X framework, that unified container is the B4XDaisyDrawer class. It acts as a single, mathematically driven script that dictates all screen geometry for both the rail and the tree patterns. This diagram shows the two UI endpoints. On the left, the navigation rail relies on a thin icon strip toggling into a wider menu. On the right, the tree layout demands wide horizontal real estate to accommodate expanding nested folders. If we strip away the typography and colors, the raw skeletal architecture remains. Both the rail and the tree are constructed upon the exact same geometric bounding boxes, an M left panel boundary for navigation and an M center panel for the payload. By isolating a handful of Boolean toggles and width specifications, the B4X framework uses one single codebase to mathematically metamorphose between a deep tree menu and a persistent mini-rail. Let's trace the mechanics of the navigation rail, starting with its primary mandate, preserving the user's context in the center pane at all times. Looking at the implementation file, b4xPageDrawerRail.txt, the state is driven by user events targeting the btn toggleRail.click and toggleRailState methods. When executed, toggleRailState performs a highly localized operation. It inverts the isRailCollapsed Boolean value. This flowchart illustrates how the local Boolean is passed directly into the drawer engine's setIsCollapsed method. The layout engine catches that variable and immediately hot swaps the width of the active left boundary. Mathematically, the framework drops the active boundary down from a normal width of 300 density-independent pixels to a collapse width of just 60 pixels. The layout engine executes this x-axis recalculation through the SetSideWidthAnimated method, redrawing the boundaries smoothly. Simultaneously, the engine analyzes the effect on the M center panel starting x-coordinate. It shifts the center payload horizontally so it directly abuts the new 60-pixel rail. Notice that the boundary actively shifts instead of simply covering up the content. The drawer never overlaps the center screen. Manipulating these x-coordinate boundaries fulfills the core UX advantage of the rail pattern, maximizing primary payload visibility while the user actively navigates top-level options. That shifting layout logic relies on desktop or tablet displays.
We have to handle responsive constraints for mobile devices, where horizontal screen real estate is insufficient for a side-by-side rail. The implementation code solves this by routing the btn toggledock.click method to manipulate a Boolean named isDockedSplit. This diagram maps how the isDockedSplit state feeds directly into the foundational always-open property inside the layout engine. The internal math forks based purely on whether this property evaluates to true or false. When always open evaluates to true, the engine assumes it has pixel width to display both panels simultaneously. The setLayoutAnimated execution forces the center payload's starting x-coordinate to exactly match the left panel's width, creating a shared horizontal plane. Now trace the logic path when always open is false, the standard default for narrow screens. When this evaluation is false, the center panel ignores the left boundary and resets its x-coordinate to 0, filling the horizontal plane. To compensate, the left panel slides over the content payload into a higher z-axis layer. To delineate these stacked layers, the engine injects mDarkPanel, calculating a 40% opacity to dim the background while the left panel is active. Manipulating the always-open Boolean allows engineers to execute a transition from a flat, docked split grid into an overlapping Z-stack without ever forcing a rebuild of the DOM or the view hierarchy. When we shift to the tree drawer, constraints change. A dense folder tree abandons the Rails x-axis shifting logic and relies entirely on y-axis expansion. This wireframe displays the geometry produced by the btn expandAll.click operation. The M left panel locks to a fixed 300-pixel width, while the internal data nodes cascade vertically down the y-axis, pushing straight past the bottom boundary of the screen. This dense nested text expansion demands the use of the normal width parameter. Attempting to use a collapsed 60-pixel state would render the indented labels illegible. Because the tree's payload requires so much dedicated horizontal space to function, narrower screens default to the overlay pattern. By setting Always Open to false, the layout engine physically isolates the vertical chaos of the tree hierarchy away from the center panel's layout logic. Locking the x-axis boundaries while permitting extreme y-axis overflow allows the DrawerTree to support infinite recursive data depth without threatening the structural integrity of the base layout engine. This three-pane layout reveals the architectural loop connecting one layout engine to divergent UI endpoints, illustrating a strict separation of concerns. B4XDaisyDrawer calculates geometric boundaries, absolute offsets, and z-index hierarchies. The implementation pages, whether Rail or Tree, handle only payload logic and user experience routing. The public API mediating this relationship is intentionally minimal. Setting a single variable like setCollapseWidth reconfigures the coordinate system for the entire view hierarchy. This architectural parity simplifies cross-platform development. A single implementation handles diverse screen sizes by adjusting properties rather than rebuilding the layout engine for each device. By decoupling structural state from content, engineers can pivot between the compact rail and the hierarchical tree models to match specific data constraints, all while maintaining absolute structural stability.